So, currently at NERSC, Nick Cardo is the IBM SP project lead. Previous experience includes system programmer, system analyst at NASA Ames. And John von Neumann National Supercomputing Center in Princeton. Nick's developed a wide variety of utilities, kernel modifications, and algorithms for high-performance systems, including one of the first full production schedulers for the portable batch system PBS. So, ladies and gentlemen, Nick Cardo.
Well, that's a way old one. I'm actually working on the XT4 at Lawrence Berkeley National Lab at NERSC. And I'm going to talk to you about some file system issues that don't show up as issues. And no, I am not the 3 o'clock announcement. So the situation is file systems have problems. I don't think anybody in here will debate that one. And you'll also probably all agree that you can have problems with no errors ever being reported, which gives you two little scenarios. How do you detect a non-error problem, and how do you do it quickly? We all know Lustre will let you know when you have a problem. Just look at your messages file. In fact, on the bottom here, I did one. There were no Lustre problems during these 6 days, yet there were 5,836 Lustre error messages inside the messages file. So Lustre is not shy when it has a problem. So the focus of the rest of this is when there are no errors, how do you find a problem? So just to govern how this talk is going to go, and probably how this conference is actually going, this is a quote from Sir Henry Royce. It's all about taking what's out there, making it better, and if it's not there, create it. And that's just about what we're going to go through on my talk, as well as what everybody here is talking about. Here's a couple of useful API calls. I don't know who's looked at the Lustre API, but it's huge. But there's a lot of stuff in there. So I picked 3 of them, and I'm going to show you some easy tests you can write with these 3 calls that'll help you find problems. And at the end, I'm actually going to show you some test cases. So everybody out here probably has this little script somewhere in their arsenal. Just going out to your Lustre nodes, looking at procfs Lustre health check, seeing if it says healthy. Very simple check. But it has a problem. If the node is overwhelmed, your SSH will time out, and you may not know you have a problem. Here's a better solution, or another solution. If you write a little program that goes through procfs Lustre OSC, you can get all the OSTs for your entire file system or file systems. You can then loop through that. You can then look at all the directories in there, pass that into LLAPI ping, and you can send a Lustre ping to every one of them to see if they're alive. To put it into context, all right, here's a little snippet of source code. All it is opening the directory, looping on it, skipping ... numrefs, and then for every directory, issue a ping out there. If it fails, prints out a warning message. Very simple, very easy, and very fast. And it doesn't suffer from the problem of your Lustre node or Lustre client not being responsive. Benchmarks. Well, I went out and did a look at Wikipedia and Webster.com. And the first one is the definition of benchmark. Second one is benchmarking. Well, just want to point out a few words in there. For benchmark, it's to study. And then for benchmarking, you're looking at performance metrics, quality, and how to do things better. So if you keep this in mind, that's what we're going to move forward with the rest of this talk. And I thought I'd throw up a corollary. Benchmarks can be made to make anything look good. You can take any benchmark and it will make anything look good if you feed it the right test case. So we're not doing a performance benchmark from here forward. We're here to look at how to spot a problem using a code that gives you some performance metrics. So the first part is to create a file. Everyone here probably knows LFS, set stripe, blah, blah, blah. You can do it all from a script. Internally, you can do it from a piece of code using LLAPI file create. To read back the stripe information, it's LLAPI file get stripe. Very simple, very easy to use. Test the error codes, test to make sure that the count is correct for the number of stripes for the file you just created versus what you expected, as well as whether or not you landed on the right OST that you were expecting to land on. Putting it into context, here's a snippet of C code that does just that. You see the first line is the file create. A little further down, the get stripe, you'll see a check for the stripe count. And further down on the bottom, you'll see the check for the OST number. And now you need a write test. So you've created this file, what do you do with it? You want to stream some data to it. Essentially, collect a start time, loop on the size of the file to make sure you write enough data out to it. When you hit the right amount of data, you get the end time, compute the difference, calculate megabytes per second. Very simple, nothing fancy. One caveat, the amount of data you write must exceed your caches. If you write out 100 megabytes of file, that'll fit in a disk cache somewhere. And then you won't spot anything. So you must write out enough data to go beyond all the caches in line to the disk. That includes the cache in your controller. Otherwise, your performance is going to look great and you're never going to see any problems because you're just reading out of memory. So here's the right part of it. We're just going to use time to get the time, loop on a 1K buffer until we write the maximum size. In this case, the default is 10 gigabytes. And then we're going to take an end time, sync it, and calculate megabytes per second. Very simple, very straightforward. Read test looks really close to the right, which it is. All it is reading back that same data in the same fashion, calculating megabytes per second. And here it is. You rewind the file, get your start time, loop on it, get the end time, calculate megabytes per second. Very simple, nothing complicated. And as I said earlier, this is not a high performance benchmark. This is not meant to do that. This is meant to show problems. Now, the other scenario is, what happens if you wrote out data and read it back just fine, but what you read back isn't what you wrote? So here, you put in a little data check. Rewind the file again, loop on the file, compare the pattern to make sure it matches what you wrote. So now you're testing write performance, read performance, as well as data integrity to your test file. And here's a simple little snippet of code that does just that. See the seek back to 0 to rewind it. It loops on the file size, comparing the pattern as it reads it in. Very simple, very easy to do. Okay, so here's another little piece of code just to show you that you can do things like this. Suppose you want to know how many OSTs are in a file system. Here you're going through procfs luster LOV, read through it, find the file system you're looking for, and then you go into that file system's directory in there, and you read out the number of OSTs. It's you'll see towards the bottom where I do a P name, so I'm doing an fopen of the file in proc to read in the number of OBDs, number of objects for that file system. Very simple, very easy, and it gives you the the maximum number of OSTs in that file system. Useful if you're doing things within a program. Now, what happens if you put all these pieces together and you wrap it around an MPI code so that you can go out to all your compute nodes or some subset of them and perform a test? Here, you'll see the MPI initialization. We get the OSTs for the file system. We check to make sure that the scale of my application matches the file system. Do a create of a file, write file, read, and then verify the data. Very simple. The way this works, you allocate one task per node, per compute node, and each one of those tasks represents an OST. So each task ID is an OST number, and you just keep looping through them all. So now you're going to fan out to as wide as your file system is, and you're going to perform this test in parallel on all those nodes. So every OST will be written to at the same time. For completeness, I've included that section of code so you can actually see how that's done. There's a few command line switches included in here, such as the file system name, the size of the file you want to write. As I said, I defaulted it to 10 gigabytes, and this was from experimentation. Found that 10 gig was actually a good size to flush buffers enough that you could see problems. And you can specify what directory you're going to use on that file system to actually do the tests. So this will go out using MPI, allocate a process on each one of the nodes, and perform this test on every OST at once. It goes off and does the file creation. It does that's called the stripe file down there. That's where it's creating that file. It does the read-write test, and then inside the read-write test, it does a verify of the data as well. And then it cleans itself up at the end, and MPI terminates. Very simple, very compact piece of code. It's actually almost complete on the screens that you just saw. Now, what does it produce? Here's case number one. This machine, which is the XT4 at NERSC, has two scratch file systems, both configured identically. One has a bit more activity than the other. This was run in full production on the machine. The two top lines represent the read performance for those individual OSTs. So the y-axis is megabytes per second. The x-axis is the OST number. So each file system has 48 OSTs. And the bottom two lines represent the write performance. So here you can see that the reads are pretty close. Writes are spot on with each other. Now, as I said, this was full production. Turns out that the slower of the two file systems for read is the more heavily used file system. So it's within what I would expect to see out of the file system. This is not maximum performance. So you're seeing they're all performing relatively the same, and that's the key point to this. So now we'll look at another file system. The blank y-axis is also megabytes per second, and the blank x-axis is the OST number as well. In this case, repeated runs of this code produced this pattern, where the same OST was lower performing on reads and writes. Went through it looking for bugs in the code. This was run when the code was being developed. So it wasn't even known that there was anything wrong with the machine. Here we kept running it and getting the same one. Tried forcing it onto other nodes to see if it was a compute node that was bad. Same result. No matter what we did, got the same result. The ultimate cause for this one turned out to be a bad fiber channel cable. There were no errors on any controllers. Luster was quite happy. The only symptom was this. This piece of code was having a problem with that OST. Users weren't even complaining. They didn't even notice this. So here's a case where you found a hardware problem by running a software test. Case number 3. This is a more recent scenario. Again, left is y-axis is megabytes per second, and the x-axis is OST number. And the upper line represents read performance, lower line represents write performance. So this is the baseline. I know there's no numbers on here, but this is the next slide. You'll see a pattern shift. So these two lines are going to show up on the next slide, along with a more recent run of this. So the bottom two lines represent the read performance and the write performance. So here, there are no errors anywhere on the hardware, no errors anywhere in Luster, no errors in the system, and performance dropped. In fact, the read performance dropped below the previous value of the write performance. And the green line is the write performance, and you'll see that one spike, there's actually two spikes there. Both the read and the write spike at that point. Turns out, repeated runs of this, one of the first couple of OSTs that gets allocated will get a higher performance, but all the rest are this pretty flat, really low number. So this is a real case. The solution is not known as to what's causing this yet. So this is actually a real case under investigation. Now, as I said, it's not a performance benchmark, but by looking at the ongoing performance of what you expect to see, you can spot the anomaly in your normal data. And that's what this is doing. It found an anomaly. Performance tanked. Repeated runs were all bad, and it didn't matter where it was in the machine. And to close it out, I was inspired by Frank's talk yesterday with when he talked to the panel solution at the end. Should you buy or should you sell, should you hold? So here's my version of that same slide. And yes, that's Kennedy and thank you. But I don't know if you may not be able to read that in the back. The guy on the phone who's on hold, your call is important to us. Please stay on the line until your call is no longer important to you. With that, I'll be willing to entertain any questions and keep us back on track.
Go.
So the stuff that I do likes to look at things that are going on the back-end servers. And one of the things that's kind of hard to tease apart is when you get these sort of degraded modes of behavior that you can see in the LMT data, is it the system or is it the workload? And so one of the things that would be really valuable is to know the exact date when you fix that fiber channel cable, because then I can go and look at the before and after, and I can see.
That wasn't our site.
Oh, boogers.
That's why there's no numbers there.
Okay, well, if you do come across something like that, just pop me an email if you think of me.
Just pass it down here.
Hi, there was just one thing that looked a little strange in the last graph you showed us, was that the bottom green line was perfectly flat. Do you have any explanation for that?
It's actually not perfectly flat. It fluctuates very little, though. And when you make it into a nice graph, it flattened it. It's not a perfectly flat line, but it's within like 1 or 2 megabytes a second of each other.
So like you said, you have to go looking for these problems. How do you, can you automate these sorts of results or notifications of problems, right? I mean, you could put some sort of low watermark at performance once you've got enough data to kind of know what's good or bad, depending upon, like Andrew said, you know, what the load is on the system. But how do you normalize for those situations? Or I mean, until you just go look at the data later.
This one is actually running during full production, and I also run it in dedicated mode right after we boot the machine. And you have to be careful about that. As you know, Luster's maximum performance does not immediately show up after a boot. It has to build its tables and stuff, so it takes 1 or 2 runs to peak it. So that's a case where you have to look at the data to know what you're seeing. As for picking out problems in an automated fashion, this runs as a batch job on the Cray, and it knows an upper and lower bound. And if you're out of that bound, it will flag it. I have not seen where conflicting workloads in production caused a significant variation in these. In fact, this is a very typical run during production. So if you just make the range wide enough, you'll be able to automate it and pick out an anomaly, because you're not looking for the little change, you're looking for the big change. And I'm guessing you want to chat about something else afterwards.
I had a question. I noticed that your program kicks all this off as an MPI job, start all these simultaneously. Have you tried starting up these tests serially, or is it important to initiate tests to all OSTs at the same time in order to see these patterns, or can you do them say cycle through one by one and still get the same effect?
It changes the dynamics of the test. I've done it both ways. What's been found is that when you go one by one, you don't see any impact or any degradation as a result of doing something in aggregate. And in fact, that last case, this one, if I run it one at a time, everything looks great. It's only when you ran it in aggregate at the same time.
I'll take a stab at telling you what that problem is. Someone rewired your network, so all your traffic is going over one wire when you run them all in parallel. You do one at a time, one wire is sufficient. When you do them all in parallel, it ain't.
I can tell you that the network was not rewired.
Are you looking at the subject manager log or something like that?
Yes.